Okay, so for the first part of the session, what we're going to be having them look at is the sums of and the first n integers. So what I'm thinking is have these already arranged and have 6 different stations.
Okay.
And not just looking for what the areas would be. Here we're back to thinking about areas, not volumes, just looking at it top down. By the way, is there something I'm missing on one of these?
Yeah, there is. Let me grab
1, 2,
There's
3,
two
4, 5. So we need one more here and one more here.
Actually, so we can fix that real quick.
Yep. It didn't look like a triangular number the way the rest of them did. Okay. So rather than just getting what the total area is, adding that up real quick in their heads to get them to be looking at the rows. 1 plus 2, 1 plus 2 plus 3. Again, looking at printing out worksheets that will direct them that way. And probably have talked in advance about what's an arithmetic sequence, what's a geometric sequence. In this case, the common thing being added, of course, is just 1 each time.
Right.
Okay. And then, I'm going to pause this.
There we go.
See that? And then that'll fade out.
Okay.
Okay. So you said this was 3 by 4.
Uh-huh.
Which is 12. How's that compared to the 6?
It's double.
Double again. Okay. Next one, well, that's just going to be 4 more than the previous one, right? Okay, that's 10. All right, well, I'll do this one, and we can borrow from the others. So let's see here. 1 plus 2 plus 3 plus 4. Okay. Let's do it this way if I can. Come on. All right. And now we have a 4 by 5, right? Which is double the 10. All right. Want to make a copy of that one?
Sure. You want to switch me?
So what I was thinking of doing was with the originals, before we have them copy and arrange, to have 6 different stations that they'd go around, realizing that they're doing a sum of n positive integers, that we're doing one more term with each station that they go around, and then I'll have them go around again and have them making the copies, putting them together.
Yeah.
Or maybe like 1 to each station or something like that. So you made that copy, and we have what dimensions then?
That is 5 by 6.
Okay, which is how much?
30.
30. We had the first 4 there adding up to 10, so that's going to be 15. Versus the 5 by 6. Give me 30, twice as much as 15. Okay, so now So that should be 21, right?
Mm-hmm.
Okay. My guess is going to be we're going to have a 6 times a 7, which is 42. Taking half of that would give us the 21.
Mm-hmm.
So let me try that out. Stay. Okay. So that should now be a copy of this one, right?
Mm-hmm.
Okay. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. So the prediction was correct. Okay, now by the way, what if you put those together instead of a copy?
What? Oh no.
So that's-
Oh, you're missing. Wow.
That's the 1, 2, 3, 4, 5, 6, 7 being
Uh-huh.
added up. This is the 1, 2, 3, 4, 5, 6 being added up.
Oh, would you look at that? Nice little box.
What kind of box?
It's a cube.
Well, we're just looking at the
Oh,
top.
sorry, square. It's two-dimensional.
That'll always happen. That could be a little side thing towards the end. But, okay, it is now your responsibility to make that copy
Okay.
of that.
We got so far. 1, 2, 6, 7. I'll grab the other one there. I got you here, thank you. That's so sad. Why they gotta do me like that? Playing with Legos as a kid was so much easier. There you go.
Okay, so we'll rest it right on top just so the viewers can all see
Okay.
Dane or anybody else that happens to stumble across the video. If you take that back apart so that we can see that it was in fact a copy, if you lay it on top of it for a moment. Okay, so each is adding 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. Okay, and putting them together as a rectangle, it looked like what? What are the dimensions?
7 by 7. Right? 1, 2, 3, 4, 5, 6, 7, 8. Nope, 7 by 8.
7 by 8.
Highlight 2.
Okay, so there we go. So this is one higher,
Uh-huh.
I mean one term more.
Yeah.
So we already had from these up to 21, adding the 7 to all of that, we're up to 28.
Mm-hmm.
And if the pattern's holding true, we should be doubling that to get
56.
56, and you said the dimensions are 7 by 8.
Mm-hmm.
So 56 divided by 2, that is 28.
Yep.
Now, we would express that as n times the quantity n plus 1 all over 2,
Mm-hmm.
where n is the number of terms.
Yeah.
We're always starting with 1, and we're
Mhm.
always going up by 1. So if the first hour isn't up, as I put in the plans that I shared with you on
Mhm.
OneDrive, we could have something like, what about 5 plus 10 plus 15 plus 20, etc.
Mm-hmm.
But if it's starting with 1, look at how many things are being added. Since these are all just going up by 1s, then it's going to be number of terms times 1 more than the number of terms
Divided by 2.
In other words, n times n
Yeah.
plus 1. Because since you're starting with 1, your last term would be the nth positive integer.
Mm-hmm.
What else? And as for y, maybe even introduce this idea pretty early on. Well, we're using some smaller examples, but what if you had 50 things to add?
Right.
Or what if it were a case like 700 plus 1400 plus 2100 plus 2800 plus 3500?
Mm-hmm.
And of course somebody, I won't say any names, we know one name already, but somebody might say, oh, that's easy, it's blah, quickly adding up 700 plus 1400, whatever. Let's say, hey, everybody's going to have their limitation of how many things they want to add.
Right.
And in that case, where it was saying 700, see, that was our fourth one.
Mm-hmm.
1, 2, 3, 4. Well, if you factor out of 700, I'm trying to think of what terminology to use with them, but if everything was divided by 700,
Mm-hmm.
then we would have that, and to balance that out, multiply that by 700.
Right.
Okay. All right. Okay. So in the middle section, rather than looking at the sums of the first n positive integers, we're going to be looking at the sums of the squares, which is the reason why I'm wanting them to talk about what they know about exponents at the beginning of the whole session. And just like with this situation, there's going to be two things. Like, why would we even bother looking for the pattern? What if you had 50 or 100 or 1,000 of these things? And also the side note about what if instead you had, instead of the 1 plus 4, what if you had 50 plus 200 and so on, but say a whole bunch more terms after that. So I don't know how many terms we want to have for them, but as I was saying earlier, I think we're only going to have just one example involving the manipulators, given the number of blocks that are going to be involved. We got plenty of that. So given how many blocks would be needed for this, etc., they can just have this first example. So, now we're back to talking about volume. This one we've got 1 plus 4, or 1 squared plus 2 squared, for a total volume of 5. But we also have a total of 6 copies of that. And just like with the sums of the first n integers, where they were able to put them together to make a rectangle, certain dimensions, I want to see if we can put these together as a rectangular prism, a box of certain dimensions, and see how its volume compares to that answer. You want to try it without looking at the cheat sheet?
Sure.
Okay.
Dang it.
Well, we know what they don't know, which is that it's going to have a dimensions of 2 by 3 by 5.
Good to know. Which is what's happening. That's cool. Oh, no. 2 by 3. That's so tragic.
It's what? Tragic?
Yes, indeed. Because that should be the last. Maybe I just rotated it wrong. 4. 3.
If nothing else, this can eat up some time.
Yeah, I can, that's for sure. Oh, I think I got it. Nice. It just doesn't go together because these are that little thing right there.
So you can't get them to
But I could do this.
stick together, but
Let me do this. So you can do that. This might.
so it still looks the same after that rearrangement, but now you're trying to get them to lock?
Yeah, I'm trying to make them look like a key or a rectangle, whatever. There you go.
Okay. So again, that 2 is coming from there being 2 terms. 3 is 1 more than that. And the 5 is double how many there were plus 1. And you're getting a volume there of 30, which is 6 times bigger because we have 6 copies of that. So unless we really want to even spend more time arranging something like this, which just a single one of them would have 14 blocks,
Be a lot.
like what we have there in that diagram, and then a total of 84 being used. Again, the important part is what if you had many more terms to add? What can we do as a second side note of if there's a common factor, and when you divide that out, that you would have a sum of squares.
Right.
And I don't know that you would have ever seen this. Mr. Can I say the full name, Mr. B, or should I just keep calling you Mr. MLC Director?
You can call me Mr. B, it's fine, but
Come on out, Mr. B. I wonder if you've seen this.
what am I doing?
I want you to see something. Second differences. So it's not that we had an arithmetic sequence where we kept adding on 1 more, but if you go 2 layers deep with the sums of the squares, well, thinking about the sequence rather than the sum, that what's getting added on, if you go 2 layers deep, find the differences here, and then do the differences on the differences, that becomes constant. F of x equals x squared equals 2x.
It's like the discrete version of that.
And so that's the other thing is why all this stuff is being done overall, to make allusions to calculus applications, link it for that one student that was here last year to that activity that he experienced then, and also for all of them to financial applications, for example. The one we did with the geometric sequences connects to the formulas for amortizations, student loans, mortgages, annuities, etc. Test run, using manipulatives for the difference of squares. Okay, should I use your name or not?
Sure.
Okay, Shannon, for this thing in all orange, if you look at it from the top, what's the area?
Well, you have 3 by 3, but minus 1, so 8.
Okay, so you have 8, 3 by 3, or with what we'll be talking to them about, in the actual session late next week, 3 squared minus 1 squared. Okay, can you rearrange that? Still keeping that as 8, but make it a rectangle. Okay, so nothing added, nothing lost, just moved around. What are the dimensions?
4 by 2.
4 by 2. I think they'll know the phrase dimensions when they talk about area.
I think so.
That's what I figured. Okay, so what's the relation of the 4 and the 2 to that 3 squared minus 1 squared you were talking about?
Are you saying the 4 squared minus 2 squared, kind of like this 3 squared minus 1 squared?
We had 3 squared minus 1 squared to get that area of 8. And this still has an area of 8.
Uh-huh.
You said the dimensions are 4 by 2. How are 4 and 2?
They're doubled. 2 and 4. 4 is a double of 2.
But instead of looking at it that way, how are they related to the 3 and the 1?
They're just one step higher. So 3 goes up to 4 and 1 goes up to 2. Is that what you're going for?
Not quite, but let's try looking at this one. We can come back.
Okay.
All right, so what's the area there, if we're just looking at the top of that?
Well, you got 5 by 5, and then you're missing 4, so 21.
Okay, we have an area of 21, 5 squared minus 2 squared, and rearrange that the same way, that you get a rectangle. Okay, and what are the dimensions now?
That's 7 by 3.
Okay. Mr. MLC Director, could you take over the filming? Write some stuff over on the board. That's what we're going to do. Face it towards the board.
Board, okay.
Okay.
I'm not playing the role.
You said the dimensions were 7 by 3 when you were rearranged it, right? Okay. So we're looking for a connection between the 3 and the 1 to the 4 and the 2. We're not talking like, we're talking about that pair and this pair instead of this to this and this to this. So this is a pair to this pair. And similarly, this pair 5 and 2 in connection to that pair. So put that way. Does that give you an idea?
That pair to that pair. Well, my brain's thinking that 5 and 2 is 7 and 3 of the 1 to the 4. I don't know if that's what you're trying to deduce here. Is that? Oh, let's go. 5 minus 2 is 3. 3 minus 1 on the other side is 2.
Okay.
And then the 3 plus 1 is equal to 4.
You just discovered the difference of squares.
Let's go.
All right. I'll come back tomorrow when you've got some more time. We'll discuss the difference of cubes and the earlier stuff in this session. All right. Thank you, Mr. MLC Director, who I have not found out whether you want your name used or not, so.
Well, the camera work is not going to be very good.
I didn't realize that's what you're.
I have a stabilizer. Did you have? So when we were looking at the difference of squares there, that's the first example, not the second example, but the first one would be connected to the formula for a geometric sum, where there were just two things being added. So when we had the thing with an area of, what was it?
There was an 8 and a 21.
Okay, so the 8, we got that from 3 squared minus 1 squared. The next one and that one, you could have 1 plus 3 plus 9. And I actually have that one right here. So here's how I'm going to try phrasing this. Taking a look at this pair here, I'm not looking just for the volume, but to express that based on the layers there as things being added up and expressing those as powers. So do you think you can do that for that one?
So you're saying like,
So we've got 1 plus,
and then you go to 2 and then 4?
okay, express,
But like
so-
in powers?
yeah,
1, and then got 2 to the first part, and then you could do 2 squared. Is
Yep.
that what you're looking for?
okay. If you could hold this a moment. Guess I would need to be down here, right?
Right.
Got 1 plus 2 plus 2 squared, or 1 plus 2 plus 4, which is giving us 7. All right. Okay. So now let's take a look at the solid blue one there. And we're not looking at the layers anymore. We're looking at that in the same way that we're looking at the thing taken away. So overall, before that one spot got taken away, what's our volume?
You have the 7, wait, 2 times 2 is, yep, 7.
Okay, so 2 cubed, giving us 8,
Minus 1.
taking away the 1. Okay, I'll have you hold that again. And actually, we can express the 1 as 1 cubed.
Yep.
In that case, we're getting exactly the same thing.
Mm-hmm.
Okay. All right. So let's take a look at the next pair. That one I already gave away. That would be 1 plus 3 plus 9, or 1 plus 3 plus 3 squared. Okay. And same kind of thing there. We've got a cube with a volume of how much before you take away the,
The 27.
okay.
But then you take away 1. So 26.
Okay, so here we had 1 plus 3 squared, i.e. 1 plus 3 plus 9 for a total of 13, right?
Mm-hmm.
Okay. And the 27, express that using a power.
3 cubed.
Okay, so 3 cubed minus 1 cubed. It's going to give us 27 minus 1,
Mm-hmm.
which is 26. And is there another color here? Yes, there is. Here, let's use one that's very close to purple that probably won't show up as very different.
Right.
But 7 and 7 being exactly the same. 13 and 26 not the same.
Mm-hmm.
But we're going to take a look at one more pair here. Let me guess I'll have enough room to put it on here. Sort of, kind of.
Yeah.
All right. So again, expressing the volume of this one, similar to what we did right here and right here.
Oh gosh, 4 by 4 is 16 by 3. Lord.
There is 16 at the bottom.
21.
4.
21.
Okay. So expressing that this way,
Mm-hmm.
how would we do that?
Do you want the 4 squared?
That would be the last one.
Uh-huh.
So 1 plus 4 plus 4,
4 squared.
For a total of 21. Okay. And then that one. Okay, so we're,
times 4 times 4 is 64, so then 63. Right? Did I do my math right there?
mm-hmm.
Cool.
Okay, get all that again. All right, so we've got 4 cubed minus 1 cubed.
Uh-huh.
64 minus 1, 63. All right.
Mm.
So this pair
Stayed the same.
got exactly the same.
Mm-hmm.
How are 13 and 26 connected?
Doubled.
Okay. 13 times 2 would get us 26.
Mm-hmm.
Okay.
Mm.
And we're going to look at one more here in a moment.
Mm-hmm.
But similar to how, with the difference of squares, well, I'll hold off for a moment.
Mhm.
Does 21 go into 63?
It's tripled.
Okay, 21 times 3, giving us 63. Okay. Just like with the difference of squares, we're looking to write this as a product of two things.
Mm-hmm.
The fact that this stayed the same,
Uh-huh.
we could say that we'd multiply it by 1.
Mm-hmm.
Any idea why, when the common ratio that we would multiply, in that first example, that was 2,
Mm-hmm.
that we're multiplying by 1 here. Here our common ratio is 3,
Mm-hmm.
we're multiplying by 2. And our common ratio here is 4, we're multiplying by 3.
Yeah. N minus 1.
Okay, so it's 1 less than what that common ratio is.
Right.
So formulaically, what we're getting is, not that we'll express it this way with them,
Right.
probably be something expressed in words, but the geometric sum part that we're looking for here, this part,
Mm-hmm.
you're multiplying by 1 less than the ratio, and we're getting x cubed minus 1 cubed, or just x cubed minus 1. You could actually generalize that to a difference of 2 cubes formula, but
Mm-hmm.
we're just concerned with then turning that into, we'll be letting them know that that's what we're focused on.
Mm-hmm.
So just like x plus 1 would be x squared minus 1 over x minus 1. As long as you're not using a ratio of 1, if your ratio is 1, you're just getting a constant sequence, not
Yeah.
a geometric sequence. And also you would be dividing by 0. But getting a formula here for the geometric sums with 2 terms, with 3 terms. We wouldn't be able to talk about 4 terms with this kind of presentation, because then you'd have to be able to make something 4-dimensional.
Right.
But maybe they could express in words, well, if we have this many terms to add up, where we keep getting the next term was multiplied by some common ratio, that number of terms is shown up here. So you've got the power, you take that common ratio based on how many terms there are, minus 1 all over the common ratio minus 1. See if they can get that, but even if not, even if we only get so far, maybe the first 2 things will take quite a while anyway. But that's the plan for the geometric sums.